Okay, so hello everyone. Thank you for joining me here. I'm really happy to have the opportunity to start this track today. And even though it doesn't explicitly say it in the title, this talk will be about AI. And we'll talk about AI from two different perspectives. So first of all, I would like to tell you something about a thing called continual learning, which in my opinion is really, really important thing. But I have a feeling that it's not so hyped and people don't talk about it that much. And I would also like to show you some real-life example from the medical field where AI can really make a change. And I would like to tell you this in 3.5-act story. So a few words about myself. Why am I standing here and talking to you about AI? I worked as a CTO and AI solutions architect at the Blue AI, where we are developing customized AI solutions for companies from various industries. I have been working in AI for over the last 8 years now, so this has been really a fascinating thing to see how the role of AI expert is changing, like from nerdy scientist 8 years ago towards an influencer nowadays. So this really has been an amazing journey with that. So during these 8 years, I have the opportunity to work with many different companies to deploy very different solutions using AI to help them solve different challenges. But what is important for this talk is that together with our team, we have worked a lot in the medical sector, helping to solve the challenges of recognizing different structures on medical images, working together with a medtech company to deploy them at the end. So just to give you a quick overview about what kind of projects we have been conducting. So we have been recognizing different structures. So here, as you can see, these are the bone structure based on MRI pictures. But we also developed more advanced solutions, for example, to recognize ventricles in the brain, which you can see as the red dots in here. Right now, we're also working on liver segmentation. And this is quite a tricky one because apart from recognizing the liver itself, it's really crucial to recognize the vein in the liver. So they're really not that easily seen, but it's super crucial to recognize them because if you're doing liver resection, you cannot cut them because that would be really, really bad for the patient. And the nice thing about it, so if we already developed the models and recognize the structures, we are working with a partner who is building extended reality solutions. So all of that can be used by the doctor using HoloLens glasses or MetaQuest glasses, in which they can see the real data of the patients as 3D models so that they can use the pre-planning before the surgery or also use it for patient education. So with that, we come to Act 1, which is called focal cortical dysplasias. And I can already tell you that this has been one of the most challenging projects that we had in the healthcare industry. To start with, maybe let's take a look at some interesting statistics. So it is estimated that about 1% of the global population is having epilepsy, so about 50 million people, which is making it one of the most common neurological diseases globally. And as you can imagine, having epileptic seizure is really a tough thing. Like, it is really impacting the quality of life of these people. But to make it worse, it turns out that these people has also much higher risk to die unexpectedly during a phenomenon called sudden unexpected death in epilepsy patients, which happen mainly during sleep. So we can see that this is really a crucial problem, so really something that should be solved, that is really important. And if we dive a little bit into the epilepsy, sooner or later, we come to something that is called focal cortical dysplasias, which is something like that. So what are FCDs? Here we can see it under a magnifier glass. They look like that. So they are some misbuildings of the human brain. It's not fully known why do they happen. They are just some faulty brain tissues that get created. And they have very high epileptogenic potential, meaning that they are very frequent cause of epilepsies. Fortunately for some of the patients, they can just take some drugs and they can live a normal life. Everything is fine. But there is also quite a big group of the patients who are pharmacoresistant, meaning no matter of the drugs, they are still having the seizures. And for the majority of them, the reasons are FCDs. And the good thing here is that they are potentially operable, so they can have a surgery, everything will be fine. But the tricky thing here is to find them. So how do they look? On magnetic resonance imaging, because this is the way how we can see them. There are some distinct features. So a little bit tricky part here is that there are some characteristics, and for some of the patients, they will have some of them the other ones. The combinations can be very different. First of them is blurring between the gray and white matter, which you can see here on the picture, the white thing in here. Another one are the thickening of the cortex, abnormal duration, so a little bit abnormal shape of the brain, hyperintensities either of white or gray matter, sometimes quite characteristic tapering, which you can see here. And unfortunately, they can differ in size, they can be really in many different areas of the brain, and they also can differ in shape. But the good thing here is that if everything's go well, so if the epileptologist finds this FCD, the patient can undergo brain surgery, and after that, he can become seizure-free. So can live normal life, have no more risk of SUDEP, so everything's well. So right now, having all of that knowledge, I have a task for you. So if you already know what the characteristics are, here are 3 patients, and your task is to see if any of these patients has FCD, and if yes, then where. A few seconds for you. All of you are right, because all of them have FCD. But as you can see, it's not that obvious as we saw on some of the examples with blurring, etc. So it turns out that the task is really, really hard, and it requires expert knowledge of epileptologists. And as you can imagine, very expert knowledge in a very niche field is very rare. So it means they are really people who never get diagnosed. They just never have a chance to go to the epilepsy center, to get diagnosed, to have their MRIs checked, and to really know that they have it. So we had a thought, how about to use AI for that? So we developed different segmentation models. We tried to do different things, for example, detecting brain tumors or different areas. So we decided to take our knowledge in AI. We worked together with the biggest epilepsy center in Germany, which is in Hamburg. And as this is quite a complicated case, we also took Dr. Patrick House to make it even easier to solve. As an expert with 25 years of experience in there, also the name is hopefully also helping here, so that was our team. With quite, as you can imagine, working on AI, the data is everything. If you don't have the right data, trash in, trash out. So this is a really important step. So we managed to collect the biggest, to this point, data set of MRIs according to our knowledge in the world. So no one ever has published before more data set collected more patients with epilepsy in one data set. So we had 200 of them. If you are lucky enough that you never ever had any magnetic resonance in your life, then I can just tell you that usually this is just a series of pictures, so between 20 up to 500, which create the full picture of your body, like all of the inner organs, and they allow you to look through it as a 3-dimensional perspective. But we also wanted to be able to recognize when the FCD is there, and we also wanted our model to know that there are also different abnormalities in the brain. It's not only FCD, they're real life is a little bit broader. We worked here also with the T1 and FLAIR sequences, so it turns out that MRI is not just MRI, there are different kinds, and T1 and FLAIR and T2 one of the most common series. And what was very important for us, so we didn't want to show the metrics and say, hey, we're the best, we really crashed it, got XX% accuracy. We wanted to work it in the real life, so it means we got all of the data, even if the data was not optimal, even if it was hard to see, like the doctors were having some of the issues working with that, we took this data because this will happen in real life. The data will not be perfect. And we also worked quite a lot with the ground truth, meaning that we checked also post-surgery information, we checked AEG, just to really be sure that the FCD was there. Just important mark on the working with medical data set itself. So it really requires preparing the data in the right way, which is very time consuming. So on this example, we can see how usually the doctors are annotating our data, so they can see one patient in 3 perspectives. This is the same person, the same MRI, but just looking from the different perspectives. So they really pixel-wise need to adapt and say where exactly the FCD is, because it's not that easy that we just tell the AI, hey, there is some FCD in here, this is your job to tell us where it is. We really need to show it the example so that it can detect the patterns itself, and this is quite time consuming in here. So it would be really nice if we already had all of this work to annotate the data, prepare everything, so now we throw everything to the neural network. But of course we tried that, but it's not that easy. So 200 examples for such complicated problem is not enough to make it fully only using neural network. So we used something called pre-processing. So we helped the neural network a little bit by removing some information that was unnecessary. So in the first step, we decided to implement brain segmentation. So it means the skull was completely not needed. So we removed it. We just kept only the brain. For that, we use like another small neural network. Another step is morphometric analysis. So it turns out that epileptologists themselves are trying to use some more standard tools to be able to see some of the features in a little bit more obvious way. So we mentioned blurring or the hyperintensities. So there are some mathematical methods that help you expose it. So for example, when it comes to junction, it's working for intensifying even more the hyperintensity of the white and gray matter. We do that by calculating, for example, standard deviation and a few methods, and it helps us to see a little bit clearer that, hey, that's some hyperintensity in here. Similarly, we can do with the blurring. So it turns out if you have something slightly blurry and you apply lots of blur to this picture, then this original blur is getting more exposed. I also learned last week that the similar thing is being done for the pictures. Like if you would like to see where there were some changes in the picture, you can apply some additional filters to also expose the areas that has been changed. And in the third step, we did final preparation. So we did some cropping, padding, standard operations. We combined the original T1 and flare and added this junction and extension. So now is the moment for the neural network architecture. So we really tried a lot of different approaches. I will not mention all of them here, but just the final one. But just to say, we also did something that usually in AI you try to do. So meaning, if you had a similar problem in the past, you try to use that knowledge and to train the model on a little bit slightly different task. But it turns out it didn't work. So we used some brain tumor segmentation task, but this one was completely different, so it didn't work. So we implemented, this is a simplified version of the architecture that we used. This is based on an encoder-decoder architecture. So without going into too much details, the main idea behind the encoder-decoder is that we take the original inputs and we try to compress it. So meaning from the very big picture, we try to go down to very small representation in there. And then in the decoder step, from this very small representation, we try to go back. So we try to recreate the original size of the images. And what turns out is that in order to do this in a way that we are still able to condensate, to have all of this knowledge in here, the neural network really needs to recognize the crucial things that are for solving the problem. So for our case, for detecting this FCD in here. And for that, we can use skip connections, which are just helping to show the original images to have more fine-grained detail visible in there. In our case, we also added additional regularization method, but this was just for preventing overfitting of the whole model. Metrics and results. So we try to look at this problem from two perspectives. So first of all, it's obvious, like every time you look at the precision recall, you just want to know if you detected how many patients actually had the FCD, how many not. But very important for that was also looking at the explainability. So we wanted to see which pixels or which voxels. So voxel are a three-dimensional thing, like in 2D you have pixels, in 3D you have voxels. So this is the same concept. We always wanted to know why actually the neural network did this decision, like what was the region that was suggested by the neural network to have the FCD. So we did many experiments, but this one, like, it was just about the number of normal MRIs used, and we get quite nice results. So we got like 70% of recall, so meaning that we detected more or less 70% of the FCDs that were there. Precision was the level of 54, meaning that it was not creating that many false positives. Everything's fine, but we wanted to test it in the real medical settings. So we conducted the clinical validation. There were new patients, new data. We just gave our model to the doctors and they were testing it next to their usual work. These are the results, but there are two important information that I would like to show to you. First of them is the number of positive FCD findings. So this is our grand truth. In the middle column, we see that the grand truth, so we see that there were 9 FCDs in reality. On the left-hand side, we see what the neurologists did. So neurologists have expertise in a similar field, but they are not really expert in epilepsy in this narrow field. So they were able to detect 3 of them. And our model was able to detect 7. So this is already quite nice result. But there is another interesting information in here. We got the 77.8 sensitivity, cool, but the specificity was very low. It was only 5.5%. So it means that our model was quite frequently saying that there is an FCD where in reality there wasn't. So that was kind of confusing for us, so we dived a little bit deeper and tried to understand what happened. If we didn't take this voxel-based approach, you could say, well, maybe a model was always saying that there is an FCD in there. The probability would be very high then, according to your data distribution. But it turns out that our model, quite frequently, when it was making false positives, it said that there are 2 or 3 FCDs in one MRI series. This is possible. This can happen, but this is very rare. So this was already a little bit strange. And where we looked at the findings where the model said there is only 1 FCD in there, it was right in 85% of the cases. Why? So we analyzed all of these examples, and it turns out that our models was looking very much at the artifact. So if someone moved their head during making of the MRI, there was an artifact, the model was reacting to it, so this was some abnormality. Another very interesting feature is that I told you about these different features, right? About blurring, about the hyperintensity, and so on and so forth. And it turns out that the model recognized that. But as I told you, it doesn't always mean that blurring means always FCD. So it's one of the possible features, but the life is a little bit more complicated. So the model had the direction was good, but there was some still thing missing in here. And we also saw that there were some issues with regards to the distribution. So our model was detecting more FCDs in some areas of the brain, whereas in some it was more problematic. So to sum up the first act, we stand here with some challenges. So first of them is that we have quite high false positive rates. Even though we had that, so the doctors we were working with, they said it's really nice tool to make the pre-screening. So it means the model suggests me this is the region where there is a high probability that there is an FCD, so it already is helpful. But if it's giving you too many false positives, then you don't rely on that too much. So we had a feeling we should do something about it. Next thing is that we collected all of the data in one hospital. So we used only one MRI machine to do it. If you go to another epilepsy center, if you go to another doctor, there can be another machine that is creating slightly different data. Next, that it will be important for our next part of the story, medical data sensitive. Quite obvious, but this will be important. And if you try to do something in the medical sector, developing software or especially developing AI, medical certification process is really important thing that you need to keep in mind. There are really many limitations that you really need to describe, conduct, carry about. So with that, we are wondering about what to do next. Maybe we should do some different trainings. And we came across something that was more and more popular at this time, which was called continual learning. So let's explore together what continual learning is in this part of the presentation. But before we do that, just a short review so that we are all on the same page. Let's take a look, simplified, how a typical machine learning task looks. So what is the first step when you do it? It's of course analyzing the problem to understand it better. Then we create our data set, so we collect the data, we label them, pre-process them a bit. We train our models, see how do they look, do some evaluations. When we are happy, we deploy them in production. Happy end. Everything's working, everyone is happy, right? Is it? Well, this is an issue that is where AI projects are different from the standard software development. And this is specifically connected to something called data drift, which means even though we are today deploying our model to production, everything's working fine, but in some point of time soon, the model can decrease its performance. And quite frequently, this is a data drift, so it means the data distribution is changing. Assuming, for example, you're making recommendations based on the user behavior. People will change their behavior slightly in some time, and you didn't have this information in your model originally. Or maybe you're detecting frauds in financial data. So, well, these people will change their behavior so that you don't detect them, right? Or if you're working with images, the technology will change, so the quality of the pictures will be different. There maybe will be some different characteristics of the input data. Then, nextly, well, maybe after some time we have a great model, it works really well. For example, FCD, like if we already have this model and we see there were some different pathologies in there, why not detecting these different pathologies as well as a new class, instead of like doing something from the scratch? Maybe we would like to use the knowledge of this model to use it for the different new task. There will be definitely some bias in the data. So in our example, this was, for example, this one scanner that we used. So if we'll have another data from another hospital, we will see that it works very well for this one particular scanner, but the other ones can have some problems. Or maybe we train our model for some specific people, a specific group one, and for another group it will not work that well. So in general, the performance of our model most probably will decrease over time. What we can do about it? So the first thought of people working in AI will be transfer learning. So let's analyze it on an easy example. Let's assume that you have pets, and you would like to show the pictures of your pets to your friends, but it takes too long time for you to find it. So then you decide to train an AI model for that. So you collect the data from your cat and your dog, train a neural network, and then bam, it works really nice. Great. But you have a moment of weakness and you buy a guinea pig. And then your pet classifier doesn't work well because it's discriminating a guinea pig from your model because it never saw any guinea pigs before. So what you do in this moment is you decide, okay, I'll just take my model, get the pictures of my guinea pig, and train it further, and then I will have a nice classifier for all 3 pets. But what happens is that if you start training your model for the initial 2 animals, it goes to the really nice quality quite quickly, everything's working great. But the model doesn't know anything about guinea pigs. And in the model, when you take the ready model and you feed it with the guinea pigs picture, you have a really great guinea pig classifier. But the performance of the dog and the cat is quite drastically decreasing. And this thing is called catastrophic forgetting. And this is a really important thing if you try to do, if you try to learn the task sequentially. And this is the underlying thing why continual learning actually was created. So another method that you can think of is, all right, then I will just take all of the data, create one data set, and train again my classifier with all of my pets. And it will work good. So it turns out this is optimal solution for this case. But if you're thinking of business or healthcare or any other more real-life examples, there are some issues with it. Meaning that you cannot always keep all of your data for how long you want. For example, in healthcare, you cannot just for many, many years keep the data of the patients just because maybe at some points you'll want to retrain your model. Another thing is the cost of computation. So, okay, the pet classifier is really small, but if you're thinking about large language models or other models that cost millions of dollars to retrain, each retraining is very, very costly. And you need memory, you need storage. And if we also think like another aspect that we pay more attention to in the last year is also, it's connected with energy, like you need more energy, you're creating more carbon footprint with each of the retraining. And if we are talking about really big models, this is becoming an important aspect as well. So this is where continual learning comes into play. It's also called sometimes incremental or lifelong learning. So the main promise of continual learning is, and the main idea behind this, that AI should actually adapt to the ever-changing condition. So it should behave like humans, right? I mean, we have some knowledge, we learn a new thing, we don't forget what we just learned the day before, right? Just because we learn a new thing. So the model should be also able to reuse the previously learned knowledge. When we learn a new skill, we also already base on that what we already knew before, which is making it a little bit easier. And many people claim that actually incremental learning or continual learning is actually the key aspect of intelligence. Like, how do we really can interact with the environment, learning, and keeping all of this knowledge? And this is also why many continual learning approaches are inspired by biology and how the human, or how in general, the brain also of other animals work. To make it also a little bit more graphical, so the main idea here is that instead of having the model and feeding it with data each time, the idea is that we take and train the model once and then train the model of just single pieces of data. So, but how? How we can connect that? There are a few different methods. So first of them is the regularization-based approach. Meaning that, as you can imagine, when you train a neural network, there are some weights in there which you are training. So during the training, you set some values to this weights. And if you are like retraining in this transfer learning approach, then you're just changing the weights. That's why the model is decreasing its performance, because you're changing what it already learned and what was important for the previous task. So the main idea of regularization-based approach is that you try to keep these changes that were important to this model, and don't change them, just use different neurons and adapt the weights of the different neurons there so that you still can do all of the tasks on a good level. And why regularization? So we just basically apply a penalty to our loss function when you're training neural network. And we can also, like, there are very many different methods in which we can calculate which neurons were important for the previous task. And then if the networks try to change them, penalize it, so it really tries not to do it. And I said that there are quite many analogies to neuroscience, and this method has been also inspired by that. So the researchers were looking of how mice are learning. And then they saw that if mice were having a new skill, learning a new thing, then the neurons were connecting, and the synapses that were created during this process, they got like thicker, and it was more difficult to change them. So it was something that the brain was preventing from changing these neurons and from changing this connection. And with this approach, we are also trying to mimic this mechanism. So we are trying to prevent these learned skills to be changed by the new tasks. Unfortunately, this method is not perfect. Like each of these methods will have its advantages and disadvantages. So in this one, we cannot say that the forgetting will be completely solved, but it can definitely help. And another thing is that it works quite well for similar tasks. So, for example, if you're having different data distribution, these methods should work quite nicely. Another area is the replay or memory-based method. So, the assumption here is that if we are learning if the model is learning a new task, we just can remind him, hey, we had this previous task, it was also important, so try to keep it in mind that you still need to do this. And we do that in a way that we keep some of the data from the previous task in memory and we use it for training. This is also inspired by neuroscience, and specifically this is a little bit compared to dreaming. Like there is a cognitive function of dreaming for people, right? So if we learn a lot, then our brain is repeating this information, making a replay during the dream, so that we can build the new skills, so that we can retain this new knowledge. And the whole idea is that we also try to mimic this in continual learning. There's also some limitations in here. So it means we cannot just keep, I don't know, the whole internet in the memory so that we can just reuse it during the training of a new skill. And on the other hand, we still have data privacy issues, right? So if my worry was I don't want to keep healthcare data for forever, well, it doesn't solve my issue here, right? So because I still need to have some subset of the data that I'll use. But there's an interesting solution to this particular thing. So people came up also with the idea, how about training a generative model? So we get this data, we train a model to create fake data that looks very similar to these original ones. So there is no data privacy issue in here. So this is also quite interesting technique that could be used in here. And the last area that I would like to mention are the architecture-based solutions. So it relies on the way that we can design the architecture of the neural network in a way that they will not reuse the same weights. Or, for example, this will be some part of the neural net for this task, some of it for this. Maybe this will be separate layers. Maybe it will reuse some knowledge, but just the last layers will be dedicated to different tasks. Another area that is also based on architecture is that we can add new neurons or new layers when we are learning the new skills, so that the whole architecture becomes a little bit bigger with the new skills in there. And there is also inspiration from biology for that, which relies on the neurogenesis. So when the brain is creating new neurons, also when we're adults, these are mainly created in the areas where we need them most to learn the new skills. And there is one very important assumption for that. So in order to that, we can adapt our architecture to do it. It means that we really need to know these tasks, and we need to know when exactly we are doing which task, which is not that obvious for many cases. So with that, let's come back to our initial issue with FCDs. Having all of this knowledge, I think we can also find some similarities where it could be used. So we decided to tackle this challenge again and to train our neural network once more, this time using continual learning. So we created the data sets, which was coming from all epilepsy-centered patients in 2022. And we used in total here completely different distribution of data. So it means instead of having mainly FCDs, right now FCDs are only 10%. So this is mimicking the real distribution of all of the patients that are treated there. So we had 30 FCDs, 150 normal MRIs, and 120 different pathologies than FCDs. And we divided them into 3 different data sets, which will be used in a minute for training the model in a continual learning manner. So here we decided to use the regularization-based approach because this was still a very similar area, but just the distribution of the data was different. So the training phase. We started with having the model that we trained in Act 1. So it was all the same. And we used this model with the initial 100 data that we had just to evaluate it. Then we checked 2 things. First of them was, we wanted to have a comparison to what if we took all of this data and we just retrain it like from the previous model, like using all of the data that we had so far. And in the second approach, we just used purely continual learning. We wanted to also see if there will be some bigger differences and results here. So in here, we took the baseline data set, so the data set from the Act 1. We added the 100 data here, trained the model, and got the first model in here. And here we just took this 100 MRIs from this phase, and we trained it in a continual learning approach with the regularization. Then in the next phase, we took the next 100, and we started with evaluating the models from the previous phase. So we had our baseline, we had the new model trained on everything, and then we had the continually learned approach. And in the same time, we reused the data to train the next round. So again, we used our baseline, the data set number 1, and then we added also the next 100 data set here, retrained the model, got the new version, and then here we just used the 100 new pictures and train our previous continual learning method-based model and retrained it on this. And the last group of data we just used for evaluation. So what were the results here? The results were, to be honest, quite astonishing from us because we didn't expect that it would work so well. So first thing that we can see is that the baseline model, which was already detecting the FCDs quite well, it still did it. So after the 3rd phase, it recognized 9 out of 10 FCDs, which is really nice. But it still lacked the specificity, so it was very frequently saying that there is FCD even though there wasn't. The next method where we used all of the data, so we didn't consider this data privacy thing, like we could use the data to train the model at this point. It detected 100% of the cases, and it got 56% of the specificity. So the new distribution helped here to solve the problem. But what we saw in the continually learned approach is, even though it recognized 9 out of 10, so this is still great, and this one, actually, after talking with the doctors we're working with, they said it was not so tremendous difference because the data set was not so big so that we can like very stick to this one particular case that was different. But it got the specificity of 70%, which is very high as for this kind of problems. And again, we wanted to understand why, what happened here. And another interesting thing is that most of the false positive clusters that were found, they actually were detecting different pathologies. So if we were about just to have some nice metrics to write a scientific paper and to say we're the best, we just would exclude it like people usually do that, right? The main task is to just detect FCDs and not to try to mimic that there are some more complications in the real life. So if we did that, we even had the specificity of 90%, which is super high for this problem. And we also saw that while learning, the model also was coping better with the issue of distribution, so there were no areas in the brain that was particularly affected by false positives. So to sum up here, we can have a few thoughts. So first of all, we can see that machine learning is really useful for solving even complicated problems where pattern recognition is problematic for humans. So it can help us to give superpowers to these few niche experts who now can do the work much faster. Then we can also see that the ongoing training on the real-world data was continuously improving the results, and it was addressing the problem of the catastrophic forgetting thing. But another area is that also please keep in mind that there are many different continual learning methods which work best in many different situations. And I think what is really nice is that we really can see that machine learning can help in very important issue for our society, such as the underutilization of epileptic surgery in patients who are resistant to drugs. If you would like to know more, we had 2 scientific publications which were published in Epilepsy Research. So this is one of the main journals in this field of epilepsy. So the first one was the Act 1 thing, so our first approach, and the second one is focusing on the continual learning. While preparing for the presentation, I just had a nice thought that actually if you're working in AI, this is quite normal to publish in scientific publications, whereas this is probably quite weird for the majority of AI tasks, but this is probably also one of the differences working in here. But I said there will be 3.5 acts, so here comes the small bonus. Probably some of you, while hearing about continual learning, you are also having this thought, okay, like fine for detecting FCDs, but how does it translate to large language models? Like how we can use it? Is it used at all? And it turns out this is also quite active area of research right now. And this area is not so easy. So using continual learning for large language models is complicated from a few perspectives. So first of all, it's hard to say that they are doing one specific task, right? So we want them to do from definition quite many different things. So for example, this is a problematic area. To solve it from this architecture-based approach, well, we need to know the tasks. But there is also another thing, like large language models, it's not just one model and done. So there are also a few steps that we could train continually. So we could take the continuous pre-training, meaning we would like to just add the new data from last year, what happened, so that we don't need to have the whole retraining of the whole model from scratch. So this is the first step that could be done. But another thing is, as you know, large language models are as well trained to follow the instructions. So there was really additional steps in which humans were saying the preferences, and then additional training of this model is done so that they follow and they answer the questions in the way that we want them to do. So this is another area that could be continual instruction tuning approach in here. And the third approach, that's the third area that we can think about, is also that this model should behave and they should actually create content that is in line with the human values. So we also can think of continual alignment in here. So it turns out it's not that easy if you try to touch some of these components, because if you try to adapt one of them, it can completely destroy the whole. So it's quite complicated from this area as well. But from my personal point of view, I really do believe that the promise of continual learning, so the fact that AI, to be able to call it that is intelligent, it actually should be able to adapt, right? It should be able to learn from what it already had. And it should be able to learn these new skills without all of this computational costs. And whereas maybe not necessarily it will be the LLMs that will be able to deliver on this promise, I do think that this is really important part, and that the really next great achievements in AI really will be connected with achieving the continual learning promises and to delivering on that. And with that, thank you for your attention. I hope you enjoy it, and that you will enjoy also the rest of the conference today.